OK，好的，开始喽。今天的书是一样的，不过对，就开始吧。没什么，先开始再说。没错。上一次呢，我们看到了第61页。61页是 3.5 normal and joint normal distributions。那我们从这里开始。 早安，我今天有开聊天室的，赞，没错。你的你提供的书单呢？哎，我这边先跟你讲，哈哈，趁你还在，我在我在 Amazon 上面看到它其实没有很贵，所以我就买了，哈哈哈哈。等它到了之后，我们就可以换到你的书单去，我们可以就是先看，我不知道它什么时候会到，就是了。 说全世界都在等川普4月2号要讲什么。对啊，有趣，他就是要征关税嘛。嗯，不知道不知道实施下去之后会发生什么事。嘿嘿。 对啊，现在好像不是一个好的投资时期。我不知道哎，也有很多人在炒股啊，不是很多人在炒特斯拉底嘛，看它到底什么时候有料。我没有特别研究这些金融上的东西啦，就是随便看看，随便讲讲。怎么样？该不会你被套牢了吧？ OK， so yeah， 你今天读完了，时间差不多了，来哦，我来看看我从第几页读到第几页。From which page to which page? I'll say to 74, but I skip all the exercise as usual. Yeah, skip all the exercise here. So, like, let me. Let me summarize what I read just now. So, the section what I read is are 3.5. That is about normal and joint normal distribution. And then we go through to the 2.6 random process, and we stop. Just finish 3.6. So although we are like stay in the turbulence flows field, but at this point, I cannot figure out why we dig into the probability and like a distribution probability analysis statistic. It said that for chapter 3, its name is the statistical description of turbulent flows. So yeah, I don't know if this is just a description, or we will have a different kind of different kind of implement that can be used by using these methods, using this like a PD probability density function, the distribution, and random process, etc. Because in my knowledge or in my mind, so yeah, you can just treat me as a guy that I just studied for fluid mechanics after the fluid mechanics class, and then jump into the turbulence flow. I'm a little bit confused. Why chapter 3 is here? Yeah, I have some, yes. So for now, it's like session for me to summarize what I just read in the previous hours, right? So that's just same as yesterday's. But never mind, like we can still go through the statistic things. I do study like some engineering statistics, but I'm not very good at it. So it costs me a lot of time to comprehend that what is a joint normal distribution or what is a joint distribution. So like you probably will make two probabilities together and check if they are related or not. Yeah. So for this time, I focus on the normal distribution. So from at the beginning, they introduce our central limit theorem. So for the central limit theorem, you can go to Wikipedia or to get a further explanation. But for me, I'm just like simply to say the central limit theory is like when you if you take a large number of the random samples for any population or any kind of things, but you should have a finite mean and a finite variance. So the sampling distribution will approximate to the normal distribution as long as you get enough or I can say not enough, a large group of the sample, and you will get into the normal distribution approximately to the normal distribution. So that is what the central limit theorem say. Yeah. And so in yesterday's context that we are talking about, a flow can be like we can just specify that the flow velocity. Okay, so the flow velocity it can change from one experiment to another experiment. But all these experiments are the same repeatable turbulence flow experiment. Yeah. So as what I mentioned yesterday, so we will have ensemble averages. So we take the ensemble average here for over repetition. Yeah. So we can get a let's see. So we can get a case 1, case 2, and case 3, and make all these kind of things like into one. That's a bad skill of explanation, but whatever. So you just as you're saying, like you take the average, you make a lot of the number into one number. So the ensemble average is like at point 1, or like every like you got the data from the first trial, and got the second trial, you got a set of data, and you take the average from the first set and the second set to the final set, and you will get, eventually you will put a lot of the set into one set. That is an ensemble average. Yeah. Mm-hmm. So where am I? Yeah. So for flow, like if you consider in like a three-dimensional flow, U1, U2, and U3, or different kinds of things, different kind of the components you can just assume by yourself. But for this place, I use a velocity here, and you could say that you could get U1, that is a distribution, U2, that is another distribution, U3 is another distribution. So we want to make these three distributions into like to see what is the relationship between them. So we use like a joint normal distribution to regulate it. Yeah, I don't know if I said this proper correctly, but that is my understanding. Just to put all different dimensions, uh, uh, different dimensional components, and each dimension will have a distribution, and we put all the distribution together to make it a joint uh, joint distribution, joint normal distribution. So in this textbook, it introduced some probabilities of the joint normal distribution. Yeah. Mm-hmm. And yeah. And then we turn into the random process. So that is the place that I'm confusing, because yeah, you introduce an I let's change change the subject. So this will introduce a distribution, join the normal distribution, and then it comes to a random process here. But I I cannot see like Okay, sorry, so in the random process that we it change a way to make it an ensemble. Like so, you want to introduce the random process is like so for now we have a turbulence flow, right? And we did the time into your experiment. So before we get into the random process, that the term process, we just look at a point, like we have a point of the velocity. But for the random process, like you have a time series of the velocity. Okay, so from t equals to 1 to 2 equals to 10 seconds. And if your sample rate is 1 second, you will have 10 data points here. And in this 10 data, or for this 10 data point, we will have all different magnitude of the velocity, and every velocity is like a random process. It's like a random one. So like you take numerous experiments like 1 to 100 to n. So u1 at time equals to time step equal to 1 second, and u2 at time equals to 1 second to the infinity to 100 to n. You will have a set of the data that is all at the time 1 time equals to 1 second. Yeah. So and this data at so many u values in time step at t equals to 1 second will form a distribution. But at t equals 2 seconds, you will have formed another distribution. So for the random process, you get countless distribution, and each distribution they will call it as a one-time distribution, one-time probability. So what is a sorry, I'm just got cold. Yeah. So they use like a one-time CDF and one-time PDF. These kind of things to describe this. Yeah. So, yeah. So then if you put all these probability distribution together, you will get an n-time joined CDF or for a random process. Yeah. Yeah. I hope my understanding is correct. After that, it introduced a concept that is called statistical stationary. For the statistical stationary is that for this process, uh, you probably like that. Uh, so we have a joint like a joined CDF, right? So and at time at time t, for like let's say we have a joint uh, probability, a joint distribution from time t equals to 1 to time equals to 10 seconds. And what is the meaning of the statistically stationary is if you move this time interval, like I did some positive time interval into this. Like if it becomes to 6, like for the previous one is 1 to 10, right? We make it into 6 to 15, 16. Okay, so the join distribution you get will be the same. So it sounds like very arbitrary, but yeah. Yes. So because I'll say that then probably you can use another way to think about that is like if you think about a laminar flow. So for after a laminar flow that it has been initiated, it can reach a steady state, so that the flow variables will be independent of time. And for the turbulent flow that's reached the statistical stationary state, so this statistical stationary state turbulence flow will be independent of time. So no matter how you increase your time interval, the behavior of this turbulence flow will be the same. Yeah. So if we want to reach this kind of like a stationary statistic process, so you can use you can like considering the a multiple time statistic that is you can think about there is a way to see, okay, so we want to reach this like a steady state like process is independent of time, right? So you should get so you oh, okay, the the relationship here I cannot figure that much, even though the process for I can just read out the sentence here that is said for a statistically stationary process, a simplest multiple time statistic that can be considered is the autocovariance. So another way to call it is like a normalized form is an autocorrelation function. So in my knowledge, is the autocorrelation function is for time step t and time step another time step, like I can say time step t plus s. And so the magnitude for time t and time t plus s, and you make these two magnitude you into a correlation function, but these two are the same parameters. So you make these two compared by themselves. Yeah, this is called autocorrelation. So bad. Yeah. Anyway, yeah. So that yeah. That is the way I think about what is the autocorrelation. So we have the autocorrelation function here. So consequently, if you reach a statistically stationary state, your autocorrelation function should be oh, it didn't say if you it doesn't say if you reach the autocorrelation, if you reach the stationary state, what will happen to the autocorrelation function? It should be like to a finite value. Yeah, so they expect the correlation to diminish after times a leg time s, which the time leg s you can just think about it needs a time interval for this flow to reach the statistically stationary state. Yeah. So the correlation between the autocorrelation. Sorry. Maybe I should figure out why why the correlation diminish is indicated to the stationary. I probably can ask for the X ChatGPT for the answer. Yeah, but just that I'll just leave it here. I want to finish the introduction. Or no. I will finish the part what I read. No. Yeah. So this is hard, right? I just read all of these materials, but it's very hard for me to in the very short time to convert all these stuffs into my words. Yeah. But I do read the context here, and so probably that is the evidence. Is the evidence that I didn't 100% understand it. What is that? Those things going on. So for the autocovariance, so we'll use the frequency spectrum to quantify it. To well, not to quantify, just they translate these autocovariance into a frequency domain. But for now, I cannot see the advantage of using frequency domain here. Okay, that's it. I don't know how to I don't know how to express how to represent the last part of the context. So I think I understand what they want to tell, but I cannot get the logic, the logical inside the context. Is that why why introduce why introduce this now? Yeah, and it should be key part that I missed, but I cannot tell. Differentiable. Yeah, to repeat in general, the one-time PDF and autocorrelation function does not complete the categorized random process. Oh, yeah, okay. So probably you can say like the auto correlation and the and one-time PDF is a way to categorize a random process. But if you want to like we use a Gaussian process, the normal drawing normal distribution. At least for using Gaussian distribution to describe your velocity, your motion here, you probably can like get a reasonable random process here, but it should be yeah. It's saying that is what it's saying is that a Gaussian process is an important but very special case. So it's a very special case in there. So they do like a plot a spectrum there, which is very similar, to the turbulent kinetic energy spectrum. But yeah, I can only say that it's similar. I don't know exactly the point between these two figures. Yeah. Okay. Never mind. We just like ensemble, right? Ensemble. Probably is take away a message from myself, because yeah, ensemble, and how to use a distribution, statistical a distribution way to describe a random process. But what is exactly how it works on the physics it's describing, I cannot tell now. It seems that I repeat myself what again and again. But yeah, that is all I got from the previous hours. Yeah, I hope we can finish the statistical part very soon. We probably can get into the physical description here. Self-similarity. Cool. Alright. So I think that's it. So 我们今天大概就对，就播到这。其实也没有播什么东西，就是读书嘛，大家都读书，有空的话就跟着我一起读书。虽然我知道，其实对读一个没什么人在看的书，就是对，但要能理解它，其实也是很不容易。我是希望说，如果下一本书可能会好一点，我不知道，尽量吧。好，今天时间到了，那我们就先关台喽，拜拜。